Today I'm excited to present our work, GraphCAD, a novel framework that leverages graph neural networks to predict crosstalk-affected delays, post-routing. Let me start with a quick outline. I will first introduce the topic, then explain our proposed algorithm, and finally summarize the results from our experimental analysis. As manufacturing processes scale down, while dimensions shrink, but coupling capacitance between adjacent wires increases. This creates crosstalk noise, leading to two critical issues. First is the transition slowdown or speed up, which may cause signal integrity degradation. Second is about the noise bump, which may cause false switching. Traditional methods struggle with time-consuming simulations and face challenges in handling multi-input transfer functions. Meanwhile, previous learning-based works focus only on RC heuristics but lack features to model coupling effect and timing window overlaps, which is the root cause of crosstalk, while also suffering from limited methodology. Here, we see a simplified RC network. The victim net B is flanked by two aggressor nets A and C. Coupling capacitance between these wires creates unwanted interactions. However, physical proximity alone isn't enough. Timing always plays a decisive role. Crosstalk occurs only when aggressors and victims switch simultaneously. Here, from the figure, we observe that the timing windows we can observe the timing windows here. When aggressor pass transitions overlap with the victim pass signal arrivals, interference amplifies. From our analysis, two key factors drive crosstalk. First is the coupling effect from adjacent nets. Second is about the timing window overlaps between aggressors and victims. Our goal is to build a fast and accurate predictor that can capture both coupling capacitance and dynamic timing interactions. Let's dive into the technical framework of GraphCAD, starting with data preparation. First, we construct the graph by representing drivers, receivers, capacitances as nodes, and resistances as edges. From post-route spec files and prime-time non-SI mode reports, we extract the key features that capture the physical and temporal characteristics of the RC networks. These features are categorized into two types. For example, the node features, where we capture the capacitance values, input-output node counts. And for the path features, we use the incremental delays and transition times and the like. Since GraphCAD is designed with multimodal, the graph representation varies. For the HGAT model, the graph is heterogeneous, with node and edge type features to capture diverse relationships. For the graph transformer model, the graph is decoupled into uniform subgraphs, represented by a node feature matrix, an adjacency matrix, and a path feature matrix. Our final prediction objectives are while delay and slew of each pin-to-pin net, which are modeled through neural networks. Now, let's look at the GraphCAD architecture. It combines three core modules. First is the HGAT model for coupling effect analysis. Second, the graph transformer model, which used to handle wire path interactions and overlapping timing windows. And finally, we design the MLP heads for prediction here. To be specific, the HGAT model uses relation-aware attention to weigh node importance, while the graph transformer model integrates GraphSage for local feature aggregation and a transformer for path global dependencies analysis. The MLP then fuses these embeddings for prediction. This hybrid approach ensures both coupling effects and net time window overlaps can be captured efficiently. The HGAT model focuses on heterogeneous graph learning, designed to help the model understand the coupling effects between the victim net and its aggressors. It follows a two-level message aggregation chain. Intra-relation information encoding, which focuses on learning the relationship between nodes of the same type. And second is the relation-level information aggregation, which combines the embeddings from different relations to generate a comprehensive representation. For the former one, we use self-attention to learn the importance of neighboring nodes of the same type. For example, drivers, capacitors, and couplers exchange messages, which weighted by learned attention scores. This step highlights crucial neighbors that influence coupling effects. We then employ softmax to ensure attention weights are comparable across nodes. Next, the embedding of each node is produced by a weighted linear combination of its neighboring nodes within the same relation. This step aggregates information from nodes that share similar roles in the network, and then produce a meaningful representation of each node's role in the coupling effect. To generate more comprehensive node embeddings, we further apply an additional attention mechanism to aggregate relation-level information. The importance of each relation-level embedding is measured by its similarity to a shared schematic-level attention vector Q, which is consistent across all nodes and relations. For each relation, we average the importance scores of all its node embeddings, ensuring the model captures the overall significance of each relation type. And the importance scores are then normalized using softmax, and the final embedding Z are generated by fusing all relation-level information. Coupler features, which directly mediate aggressor-victim interactions, are given additional attention and concatenated to the global pool, ensuring the model focuses on the most critical nodes driving crosstalk effects. By combining intra-relation and relation-level information and emphasizing coupler nodes, the HGAT model can provide a robust understanding of how the coupling effects from aggressors influence the victim net. Next, we propose a graph transformer model to handle timing window overlaps between the victim and the aggressor nets, which includes graph stage layers to aggregate local resistance and capacitance features. And transformer layers to capture global dependencies across paths, relying on learned structural relationship without explicit positional encoding. Finally, we use a pooling module to combine the path representations and create virtual connections based on timing window overlaps. These virtual connections are determined by whether the timing window of different paths overlap, following prime times all path edge approach. For example, if the late arrival edge of a victim path overlaps with the early arrival edge of an aggressor path, we establish a virtual connection between them. These connections are then proposed using GAT layers to model the interactions between paths and measure how strongly each aggressor affects the victim. In the end, we aggregate the enhanced features of the victim net to generate the final output. Training graph CAD is challenging due to the iterative nature of crosstalk analysis. We solve this using curriculum learning. We first train on victim nets alone, and then we gradually introduce aggressors based on their overlap criticality. And finally, we scale to the full RC graphs. A customized loss function weights error by scenario complexity, ensuring more complex cases have a greater impact on the model tuning. Additionally, the optimizer's learning rate is dynamically adjusted, decreasing gradually to fine-tune parameters and improve convergence. Let's dive into our experiments. We train graph CAD on open-source designs with ASAP7 PDK, using HSpice as our ground truth. Our workflow includes logic synthesis with design compiler, physical synthesis with Innovus, and feature extraction via primetime non-SI mode. Our model was trained for 150 epochs on a single GPU, with dynamic learning rates and a batch size of 128. Now, let's look at overall performance. This table compares graph CAD against primetime, net timing, and MLP baselines. For the while delay prediction, graph CAD achieves about 90% average error, which outperforms primetime and MLP. For the slow prediction, graph CAD has 24% error, which beat all baselines, especially MLP's 51%. The delta row shows GraphCAD's superiority. 70% lower delay error than MLP and 10% lower slew error than net timing. This proves our model's ability for accurate crosstalk affected delay prediction. Also, speed matters. Here, each splice takes 285 seconds on average, which is impractical for iterative designs. GraphCAD runs in 8.6 seconds, offering a 33 times speedup. Even against prime time, we are 4 times faster. To wrap up, GraphCAD is an end-to-end GNN framework that predicts crosstalk delays by modeling both coupling effects and overlapping nets. Our innovations include we propose a heterogeneous graph HGAT model to capture aggressor-victim interactions. And we also propose a graph transformer model to analyze overlapping timing windows. And also, a curriculum learning mechanism is proposed to handle complex multi-aggressor scenarios progressively. And our experiment is validated on 7-nanometer designs. GraphCAD can reduce the errors apparently compared to baselines and achieves significant speedup over each splice. Okay, that's all for this presentation. Thank you.